Hi everyone, this is Kumar this side and welcome to Chemistry Universe. This is video number 3 of the Electrophilic Aromatic Substitution series. In the first part, we talked about what electrophilic aromatic substitution is all about and the general mechanism. The second one involved all of the major 5 reactions that we would be studying in this lesson, and we talked all of them and we did a lot of examples for them. Now this video is about the effect of a substituent on electrophilic aromatic substitution. So we're going to look at what happens to EAS when there is a group already present on benzene. So let's have a look at this. All right, so effect of substituents. So let's see the effect of substituents on EAS of an aromatic ring. Now when EAS is done on an aromatic ring with a substituent, then the substituent influences the reaction in 2 ways. Number 1, it can make the reaction happen faster or slower than what might have happened in benzene. And if it makes it happen faster, we call it as an activating group. And if it makes it slower, we call it a deactivating group. And secondly, it orients the incoming electrophile to a specific position. Now, what you need to understand here is that whenever there is a group on benzene, the way it influences electrophilic aromatic substitution is that sometimes the reaction will happen faster than benzene. In some cases, it will happen slower than benzene. Benzene is a reference. So any group that makes the reaction go faster than benzene is called an activating group. And any group that makes it go slower than benzene is called a deactivating group. At the same time, these groups also happen to orient the electrophile to specific position or positions. There are basically 2 types of groups. As I said, in one way you can classify them as activating and deactivating. In another way you can call them as ortho-para-directing, and another group being meta-directing. Now the ortho-para-directing groups are those which will orient the incoming electrophile to ortho or para. So they would orient it as much ortho as they would do para. But of course, both of them cannot form an equal amount. One will be formed more because of certain other factors, most often steric hindrance. Whereas then there is a second set, which is the meta-directing groups. So these groups will orient the electrophile towards the meta to that particular group. All right. So based on these, we can classify the groups as ortho-para and meta-directing, or as activating or deactivating. We can classify them either way. Now, what is important to understand here is that all activating groups are ortho-para-directing. The converse, however, is not true. And at the same time, all the meta-directing groups are deactivating, and the converse is not true. Now, you'll understand more of this when I show you what these groups are. So let's have a look. So I'm going to basically classify them as ortho-para, which I call as class 1, and meta, which I call as class 2. Now, in the ortho-para-directing groups, the first one we call is the strongly activating groups. Now, these groups, the strongly activating groups, besides being ortho-para, when I say strongly activating, it means that their rate of reaction when they are on benzene is several thousand times faster than benzene. So their presence will increase the electrophilic aromatic substitution by a very, very large amount. And they also happen to be ortho-para-directing. Now these groups are NH2, NHR, NR2, OH and O-. And of course, we will delve into these groups in detail. Then comes the moderately activating groups. Now these groups are not that highly activating. They will probably increase it by a few hundred times. These are NHCOR, OR, ester OCOR, or thioether, the SR. Then we have the weakly activating groups. They would increase the rate by about 10 times, 20 times or so. They are the alkyl groups, the phenyl group, the aryl group, even the vinyl group. And remember, all the 3 are ortho-para-directing. Then we have weakly deactivating groups. Now these are funny because they weakly deactivate, but somehow end up orienting the electrophile to ortho or para. These are the halogen, the nitro-NO group, the CH2X group, and the SO group. And of course, we'll find the reason why they are like that. Then comes the meta-directing groups class 2. And these have some of the strongly deactivating groups, which are so highly deactivating that virtually the reaction in some particular cases doesn't even happen. So these are the NO2 group, the NH3 plus, the ammonium ion groups, CCl3, CF3, etc. Then we have the moderately deactivating groups, the aldehyde, the ketone, the acid, the ester, cyanide, acid chloride, sulfonic acid, amide. All these groups are moderately deactivating groups. So now what we're going to do is we're going to look at least the strongly activating ones in detail. From that we'll learn quite a lot. And first of all, we'll figure out why are they strongly activating and why are they ortho-para-directing. Now I can do this in two ways. One is I can show you what happens to benzene when these groups are present and what makes them strongly activating, and at the same time what makes them ortho-para-directing. But that I can show you even before electrophile attacks. The another way, which is the better way, which is what I'm going to do, is to let the electrophile attack a particular position and then show you the arenaceous ion intermediate. And you yourself will be able to gauge which arenaceous ion would be formed more easily and why would these arenaceous ions, especially in the case of strongly activating groups, are more stable than the arenaceous ion of benzene, which is why they are activating. So I'm going to show you after the electrophile attacks, which actually is much more easier to understand and much better to figure out what happens. So let's get on with it. All right. So let's go for the strongly activating groups. And first is the, I'm taking aniline as an example. And the first I will show is the ortho attack. So this is aniline. I have the electrophile here. Let's see what happens when there is an ortho attack. So this goes to the ortho position, this takes the electrophile, and you get the arenaceous ion. Now, as you know, it will undergo resonance. And if you remember, these are the very three same resonating structures that we used to get in benzene. But look at the third one. I've also shown you the lone pair of N. And there will be a resonance between the lone pair and the empty p orbital of the carbocation. And that gives us resonating structure number 4. Now, can you figure out which of the resonating structures is most stable or least stable? Well, the most stable is the fourth one. Now, many of you are going to say, oh, the nitrogen is having positive charge and nitrogen is an electronegative element and that should not happen. Remember, here all the atoms have their octet complete. And as you know from GOC, octet completion is far more important than anything else. In fact, the positive charge that comes on N is due to coordinate bond. That is not due to electron deficiency. So it doesn't matter what kind of an atom it is. So octet completion makes this structure the most contributing structure, and it also makes the arenaceous ion extremely stable. And as you know, that in benzene, only 3 of them existed and none of them had octet complete. So this makes the ortho attack highly likely in the case of aniline. Not only highly likely in the case of aniline, but also the fact that this reaction is going to be much, much faster than any attack on benzene. Now you should also notice that these 3 resonating structures, let me show you these three resonating structures, these 3 arenaceous ions are actually less stable than the arenaceous ion of benzene. That is because in all of them, NH2 shows -I effect. And -I effect will destabilize any carbocation. So, despite having 3 resonating structures which are less stable than that of benzene, the fourth one is not only able to compensate, it is more than able to compensate and much more than able to compensate, which is why the rate is several thousand times higher than benzene. So the NH2 group destabilizes the rhenium ion due to -I, but stabilizes the rhenium ion by +M. And we know that resonance effect is stronger than the inductive effect. So the presence of NH2 group stabilizes the rhenium ion compared to the rhenium ion formed from benzene. Therefore, NH2 group is activating the ortho attack. All right, let's go for the para attack. Now, in the para attack, this pi bond will move the para. This will take up the E plus, and you get a rhenium ion like this. Now, you have resonating structure number 2, this one. And now from here, I can generate 2. One with the lone pair, octet complete, and one with the pi bond. And again, you will see there are 4 RS here. And again, you have one of them having octet complete, very similar to the ortho attack. So therefore, NH2 group not only activates ortho attack, it also activates para attack, which is why it is ortho para directing. Okay. So just like the ortho attack, NH2 also activates para attack. Now let's check the meta attack. Now if this were to attack the meta, so this pi bond will have to go here and attack the electrophile. You'll get the positive on ortho. Then this moves here, positive comes on the left side. Then this moves here and the positive comes at the bottom. Can you see you cannot get any other resonating structures? Can you also see no resonating structure is having octet complete? Now can you also understand that these 3 resonating structures of aniline, of the rhenium ion formed from aniline, are less stable than even that of benzene? Therefore, NH2 group, though it activates ortho and para, it in fact deactivates meta. The meta attack on NH2 is slower than the attack on benzene. Now one might wonder and say, okay, it activates ortho para, but deactivates meta. So why do you call it an activating group? Well, activating group means it should activate any position. If a group activates any one position, remember activate meaning faster than benzene, then we call it an activating group. We will call it deactivating only when all positions are slower than benzene. The attack on any position is going to be slower than benzene. That would be a deactivating group. So though NH2 deactivates meta, but it activates orthopara, so it's an activating group, and strongly so because of the octet complete structure, as well as the fact that it's speeding up the ortho and para attack compared to benzene. So it's both ortho para directing as well as strongly activating. In the meta attack, the positive charge does not reach the alpha carbon. Due to this, NH2 group is not able to show the plus M effect. NH2 group shows only -I effect in the meta attack, and therefore NH2 deactivates meta attack. Now, it is important to understand that all the groups that you have in the strongly activating groups, the NH2, the NHR, the NR2, the OH, all of these groups activate orthopara but deactivate meta for the same reason. Except for one group, O minus. Because O minus group on benzene is actually going to show plus I effect. So it not only stabilizes by resonance, by forming an octet complete structure, it will stabilize those other 3 RS also. The ones that NH2 was deactivating, or the one that NH2 was destabilizing. Here O minus will stabilize those 3 as well. So O minus is one of those groups which activates actually all positions. And the only reason it is orthopara directing, despite having activated all positions, is because it makes the orthopara resonating structure more stable by completing the octet. Whereas that is not able to, that O minus can't do when it is doing meta attack. Now let's compare how these groups behave. So all strongly activating groups except O minus activate ortho and para attack and deactivate meta attack. Now let's figure out the order of activating par among strongly activating groups. So my question to you is, what would you say would be NH2 compared to NHR? Which one do you think is more activating? Now, I had asked this question once in general organic chemistry when it came to basic strength. And when it came to basic strength, we said this is more basic. Now, some of you may think this is more basic because the plus I effect of R increases the electron density on N. Now, that may be a case, but that is not the reason, because for the same reason, if that were the reason, then it will also make the lone pair get delocalized more on benzene. You know, the very same reason why you say that NHR is more basic, the plus I effect of R, could also have made NH give the lone pair to benzene more, because it is increasing electron density on N. And if the lone pair gets delocalized more, it's going to be less basic. So what actually happens here is, and I have shown you this in GOC, so I'm going to show this again. So if you look at this one, this is aniline for you, okay? And there is a resonance like this happening. And of course, the nitrogen has a positive charge. I have not shown it here. So what basically happens is, this is benzene and this is the NH2 group on benzene. Now, when the lone pair resonance occurs, it occurs between the p orbital of carbon and the sp3 orbital of NH2. NH2, remember, is sp3 hybridized. Now, even though they're not exactly parallel, because this is exactly 90 degree to the plane, the lone pair, the empty orbital, whereas the lone pair is slightly tilted away, but they definitely can form pi bond. Remember, pi bond cannot form only when they are 90 degree. But what happens is, when I replace one of these hydrogens by NH2 group or by an R group, let's say CH3, look at what happens to the lone pair. Can you see it automatically tilts away? The moment I replace the H with the CH3, it tilts away. Because it tilts away, can you see its resonance with the ring will decrease? It is this fact that makes it more basic, because then it is more available to a Lewis acid. But here we are talking about the ability of N to give the electron to benzene. And as you will notice, since the lone pair tilts away, its ability to give electron to benzene will also decrease. So basically what happens is that you will find that NHR is going to be less than NH2, and therefore NR2 will be less than NHR also. Now another thing that you need to understand is, how do we compare OH? Now OH would be perhaps least activating, because O being more electronegative, it will have a greater minus I, and being more electronegative, its ability to give the lone pair also is less. So OH is less than NH2, it is less than NHR, it is less than NR2. But the most activating is O minus. One reason being that it shows plus I, besides showing plus M. And there is a second reason. If you look at the octet complete structure, in the octet complete structure, this is what will it look like. In this structure, do you notice that not only is the octet of all atoms is complete, but something unique, there is no charge. So if there is no charge, if it is neutral, it is so much more stable. I mean, it hardly looks like an intermediate. This intermediate is having octet complete as well as no charge. So O minus is several thousand times faster than benzene for this particular reason. So O minus is the most activating group of all. Alright, so this is the order, as I said. Now O minus is the most activating group. Firstly, it shows plus I unlike others. And moreover, in the structure where every atom has a complete octet, none of the atoms have any charge. The stability of this structure is more than that of the corresponding structures of all other SAG, strongly activating groups. Now, due to the plus I of O minus, it also activates meta. Can you also understand that the reason O minus is called ortho-para-directing and the reason NH2 and others are called ortho-para-directing are actually slightly different. NH2 activates ortho-para but deactivates meta. O minus activates ortho, para, meta, all of them. But it is still called ortho-para-directing because it activates ortho-para much more than it does meta. So can you see there is a difference in the two reasons? Despite the fact that both are activating, both are strongly activating, both are ortho-para-directing, the reasons are different. Okay, so it activates ortho-para attack more than meta, which is why it is categorized among ortho-para-directing groups. Now let's look at moderately activating groups. Now, in the moderately activating group, let's first look at OR. Now, as you already noticed, OH is at the end of strongly activating group. And you also saw that NHR was less activating than NH2. So it goes on to show that OR will be less than OH also for the same reason. It tilts the lone pair. Now, since OH is already at the end of strongly activating group, anything lesser than that could go to a moderately activating group category, which is what happens. So OR is less activating than OH for the same reason that NHR is less activating than NH2. And then it ends up being in the next category. The other one is NHCOR. Now NHCOR is less activating than NH2 due to lone pair double bond resonance. So what basically happens is if NHCOR is present on benzene and there is this lone pair that is supposed to go to benzene, since it is already in resonance with this double bond O, its ability to resonate with benzene will decrease. And that would make it less activating than NH2, which is why it comes under moderate. Same logic applies for the ester group. So both OR and NHCOR activate ortho-para attack but deactivate meta attack due to minus effect. And the same is true for even the ester group. The ester group, when this is attached to benzene, this lone pair is already conjugated with this double bond. So ability to resonate with the benzene ring will decrease. So the ester group is moderately activating. Another group that is moderate is SR. That is because R will anyway tilt the lone pair. And moreover, the sulfur has a lone pair in a 3p orbital. Whereas the benzene's carbon has empty 2p. So 2p, 3p overlap is less effective, which is why SR is moderate. Now let's look at the weakly activating groups. Now weakly activating groups, alkyl groups, they are all weakly because they activate by hyperconjugation as well as plus I. And since they show plus I, they will activate all positions. But their hyperconjugation works only when it is ortho and para. So they activate ortho-para more than meta. But if you take CMe3, now CMe3 cannot show hyperconjugation. So its ability to activate ortho is greater than meta and meta is greater than para. So instead of being ortho-para, it is basically ortho-meta-para. Because this can only show plus I effect. And plus I effect, it can show at ortho, meta and para that way. So it doesn't have any hyperconjugation. So if I were to show hyperconjugation of CH3, you will notice that in the ortho attack, it will go like this. Then it will go like this. And then there is hyperconjugation. So hyperconjugation only happens with CH3 at ortho and para. Now let's look at pH. Now pH is activating by plus M effect. If you look at this, let's take ortho attack. And there is these three resonating structures that happen on benzene. But can you see now there is additional structure due to the other benzene attached? So this will go like this. Then this will go like this. Then again this one like this. Can you see there are 6 resonating structures of the rhenium ion? This is 1, this is 2, this is 3, this is 4, this is 5 and this is 6. So the question is, if this is 6 resonating structure, which is greater than any of the groups that we saw so far, why is it that it is weak? Well, that is because it does not complete octet in any resonating structure. Whereas both moderate and strongly activating groups have lone pair in them, and they are able to complete the octet. This is only able to give more RS, but not octet complete structure. And sheer number does not always win when it comes to stability due to resonance. And though pH activates by plus M and has more RS than any other activating group, it is weakly activating because in none of the structures, octet of all atoms is complete. And again, pH will activate orthopara but deactivate meta due to minus I. And let's take out one more group, the vinyl group. Again, it is orthopara directing and activating. Why? Because again, it is able to show one more resonating structure than benzene. Now, these 3 were the ones that were there in benzene, but then there is this extra RS that makes the carbon, the plus get more delocalized, and therefore it is activating. So this activates orthopara by plus M. It is weak because of non-completion of octet for the same reason. And it deactivates meta by minus I effect. Now let's look at the weakly deactivating groups. Now these are weird because they are deactivating. So let's understand why are they deactivating. Well, look at halogen for example. What does halogen do? Now halogen, let's say Cl, has a lone pair. So ortho attack, the positive charge will come on to the alpha carbon effect in the end, and lone pair resonance. Meta attack, plus doesn't come anywhere. Para attack, again the plus goes to the alpha carbon and resonance happens. But if you remember, I have already told you that for halogens, the inductive effect dominates over resonance. Meaning the withdrawing effect of Cl by inductive is greater than its ability to give the electron by plus M. So if the net effect is withdrawal, then it is basically lessening the electron cloud of benzene. That would make it less reactive towards an already electron deficient electrophile. See, basically all activating groups, their purpose is to increase electron density. Because what is happening is there is benzene on one side, there is electrophile on the other side. Electrophile needs electron, and you want to make this benzene as much electron rich as possible to make it more reactive. Whereas halogen is withdrawing by minus I, releasing by plus M, but its minus I effect wins, and therefore it is net deactivating. And therefore it deactivates all positions. But it is orthopara directing because at least in orthopara attack, some amount of minus I is nullified by the plus M, where the octet gets complete. Whereas in the meta attack, it is only able to show minus I. There is no plus M there. So despite deactivating all positions, it is slightly better than orthopara, slightly better than the meta attack, because there is some amount of plus M that is shown in the ortho and para attack. And that goes for the other groups as well. You know, NO. NO has a lone pair on N. So it gives electrons. But then N and O are highly electronegative. They will pull. So strong minus I. But the minus I wins over plus M. CH2X, that was another weakly deactivating group. It has 2H for hyperconjugation, but 1X is minus I. So it gives as well as pulls, and somehow pulling seems to be greater. There is SO group. Even in the SO group, you will find there's a lone pair on S. And again, the lone pair on S is able to give electron, but S and O both being electronegative, they're able to pull, and the pull is greater than the push. And therefore, they are all weakly deactivating, yet they are orthopara directing because all of them have lone pairs. And all of them show some amount of plus M in orthopara attack. So halogen atom on a phenyl group is deactivating towards AS because it releases by resonance and withdraws by inductive. For halogens, minus I effect is stronger than plus M, so the net effect is withdrawing. Halogen atom is orthopara directing because in the meta attack it only shows minus I, while in orthopara it shows both minus I and plus M. So halogen atom deactivates all positions, but it deactivates orthopara less than meta. So look at halogen. I mean, here the reason is even weirder. O minus activated all positions, but activated orthopara more than meta. NH2 activated only orthopara but deactivated meta. Whereas this guy, Cl, is deactivating all but deactivating orthopara less than meta. So look at the difference in reasons, and yet they are all under orthopara group. CH2X is weakly deactivating and orthopara directing, deactivating because of -I and orthopara directing due to +H. And CH2X also deactivates all positions, but orthopara less than meta. Now NO is weakly deactivating and orthopara directing. The highly electronegative N and O withdraw by -I, lone pair on N releases by +M. Inductive pulling of two high electronegative atoms outweighs +M. This group deactivates all but deactivates orthopara less. The same applies for SO because it is having a lone pair. So now let's look at strongly deactivating groups. And remember, these are the groups which are so highly deactivating, they make the reaction go several hundred times slower than benzene. And because of which you will also later on find out that some reactions don't occur with strongly deactivating groups. And they are meta-directing. So let's understand why are they deactivating and why are they meta-directing. Alright, first let's look at ortho attack. Now this is NO2. I'm taking NO2 as an example, electrophile. Now first RS, second RS, and look at the third RS, how bad it is. It has got two adjacent atoms having positive charge. This is going to make this RS extremely unstable, so it will hardly contribute. So in effect, instead of 3 resonance that you have in benzene, you have only 2 RS in nitro group. And moreover, these two also are getting destabilized by the -I of strong N+. So therefore, the rhenium ion here is much less stable than that of benzene. The same will happen for para attack as well, because in the para attack also the plus will come here. Let's look at meta attack. Well, in the meta attack, what happens is that the plus never comes to the alpha carbon. And therefore, there are 3 resonating structures, albeit the fact that all the 3 are less stable than benzene, but at least the positive charge are not on adjacent atoms. So meta attack is better than orthopara attack. So can you understand that NO2 or a strongly deactivating group deactivates all positions, but deactivates orthopara more than they deactivate meta, which is why they are meta-directing. They are not meta-directing because they are meta-activating. They are meta-directing because they are meta less deactivating. So all strongly deactivating groups withdraw by strong -I effect. They are meta-directing because in orthopara attack, the alpha carbon which bears the withdrawing group becomes positively charged in 1 RS. This destabilizes the RS to the extent that it hardly contributes to the hybrid. The strongly deactivating groups also deactivate meta attack, but not as much as they deactivate orthopara attack. Therefore, these strongly deactivating groups deactivate all positions, but they deactivate orthopara more than they deactivate meta. For moderate, well, they withdraw by -M and -I. The moderately deactivating groups withdraw by -R. They are less deactivating than the strong ones as they don't have positive charge and the number of high electronegative atoms attached are less. So the moderately deactivating groups deactivate all positions, but they again deactivate orthopara more than they deactivate meta. Okay, so that is as far as the activating power and deactivating power of all those groups are concerned. Now we are going to talk about 2 things, and that is the reagents and the feasibility of reaction. Now in reagents, what we will do is we'll talk about, is there any change in reagent based on the presence of a particular group on benzene. So when there is a substituent on benzene, if it is activating or deactivating, is there any reagent change for a particular reaction, or are they same reagents as they were in benzene? And secondly, we'll also talk about whether all reactions are possible with all groups. So if a ring has a strongly activating group, then for halogenation, one doesn't need a Lewis acid along with the halogen. Now, if you remember in benzene, we needed halogen, let's say Br2 with FeCl3 or Cl2 with FeCl3. But when you have a strongly activating group, the ring is so activated, so much activated, it doesn't need any Lewis acid's help. It can make the halogen atom break by its high electron density itself, by the electromeric effect. You break it into Cl plus and Cl minus. Secondly, you'll also notice that they don't even need a polar solvent for this. You can keep the solvent as non-polar, and yet a strongly activating group can polarize the halogen molecule. So no help from the solvent is needed. Now one might ask, what happens if I do have a polar solvent? Well, first of all, it's not needed. Secondly, even with a non-polar solvent, a strongly activating group always does tri-substitution for halogenation. So if you do the halogenation of aniline in a non-polar solvent, you will get a tri-substitution, both ortho and para positions substituted. So if it can happen in a non-polar solvent, what's the point in using a polar solvent? There also it will happen the same way. So halogenation can be done by taking X2 in CS2, a non-polar solvent. In fact, even the non-polar nature of CS2, one observed tri-substitution, except OH, which is the last of the strongly activating group, which cannot do tri-substitution at least. So if you take aniline and you take bromine in CS2, it will show tri-substitution. Whereas if the same is done with phenol, the OH group, in the presence of CS2, it will show mono, para and ortho. Para will be slightly more than ortho due to steric hindrance. But OH can show tri if the solvent is slightly polar now. Here if the solvent is slightly polar, more electrophiles are produced, and therefore you will find this will show tri substitution. Alright. So now for halogenation, you don't even need a Lewis acid even if the group is moderately activating. Even with moderately activating group, water is sufficient for mono substitution. Again, it will not do tri, it will do mono substitution. For example, if you do this, you will get para and ortho. Now, in fact, NHCOR, which is another moderately activating group, you get 90% para product due to high steric hindrance of NHCOR. While for all other group, halogenation is done with FeCl3 or AlCl3. And reagents for sulphonation, nitration and alkylation remain the same, irrespective of the group. Now, let's talk about feasibility of reaction. Now, it is not possible to do Friedel-Crafts alkylation or acylation when the benzene ring is substituted with a strongly deactivating group or a strongly activating group. Now, what you need to understand is, what is the electrophile in alkylation and acylation? The electrophile in alkylation is R+, carbocation. Acylation is RC double bond O+. In fact, the acylium ion is extremely stable due to resonance. And a carbocation will rearrange also to become more stable. So basically what happens is that if you have a highly stable electrophile like a carbocation and acylium ion, since they are stable, they are not reactive. And if this ring has a strongly deactivating group, that is making benzene also become less reactive. So basically what is happening is electrophile is less reactive, ring is less reactive, so reactions are not going to happen or the yield is not going to be good. So if you have a strongly deactivating group, acylation and alkylation won't happen. But we need to figure out why does it happen with strongly activating also. Strongly activating should be able to do it faster, right? Let's check out. Now, the electrophile in alkylation and acylation are carbocations and acylium ions. These are relatively stable and therefore less reactive electrophiles. So if the ring is strongly deactivated, then such less reactive electrophiles will not give a good yield of the product. Now what happens with strongly activating group? With strongly activating groups, the lone pair of the activating atom or ion forms a coordinate bond with the Lewis acid. So what happens is the AlCl3 used for alkylation and acylation will form a coordinate bond with N, and it converts the N into a strongly deactivating group. So the atom donating the lone pair gets positively charged and consequently becomes a strongly deactivating group. And what does the strongly deactivating group do? It will not allow alkylation or acylation. So remember, Friedel-Crafts alkylation acylation won't happen if the ring has a strongly activating or a strongly deactivating group. All other reactions happen the same way. Okay, the last part is orientation of the electrophile on disubstituted benzene. Now here, let me make certain things clear. What happens is that if you have two groups, where will the third one go? Well, if you have two groups, the third one will go off, obviously depending upon where these groups are and what these groups are. But let me give you some general idea. If one group is activating and the other is deactivating, the new electrophile or the third group will always go based on the activating group. So one is activating, the other is deactivating, it will go according to activating group. If both are activating groups, but they are in different categories, strong, moderate, strong, weak, moderate, weak, they are in different categories, then the electrophile will go according to the more activating group. Makes sense? If they are activating groups, both of them, but they are in the same category, both are weak, both are strong, both are moderate, then it is impossible to predict which is major and you will get multiple products. Now, if there are two deactivating groups, where do you think the electrophile will go according to? Now, the natural logical answer would be based on the less deactivating group, right? No, it goes according to the more deactivating group. And we'll just check out why. And as I said, the positions of these groups is also important. So let's quickly check up what happens to disubstituted benzene. Okay. So the orientation of the third group depends on the nature of the two groups and the position of the two groups. So first situation is if the two groups belong to different classes, that is one belonging to class 1, other belonging to class 2, orthopara and meta. And if their orientations oppose each other, then the orientation of the group is decided with a class 1 group. Moreover, steric factors should also be considered. So for example, look at this one. Now remember, OH is orthopara directing. Ortho para directing. Whereas this is class 2, moderately deactivating group. This is meta directing. So it wants the electrophile here. Then it is decided by the class 1 group. Class 1 group is this one. So it will go based on OH, which is what we said. One activating, one deactivating goes to the activating. Now, of course, it has multiple positions to go. So it is least likely to go here due to steric hindrance from both sides. Slightly more here, but again steric hindrance of CHO. But OH offers least steric hindrance, so highest here. Now, the next one is if the two groups belong to different classes and they reinforce each other, then the third group almost entirely enters one position. Say, for example, this. Remember, Cl is class 1 and COH is class 2. But can you see Cl wants ortho, its para is blocked. This guy wants meta, again these two positions. So can you see that in this case, you will get entirely one position attack, equal likely here, equal likely here. For example, take this case. Class 1 is OH, class 2 is NO2. Now this guy wants, OH wants orthopara. This fellow wants meta, which is again these two positions. So it will entirely enter these two positions. Para will be greater as it has less steric hindrance. Now, if the two groups belong to class 1 and they have large difference in their activating power, that means they are in different categories and they oppose each other, then the third entirely group goes to the one with the higher activating power, which we already discussed. Say, for example, these two. Now, this OH wants ortho para. This CH3 wants its ortho para. This wins because it is strongly activating group. So you will have major here and a little amount here due to steric hindrance. Now, if the two groups belong to class 1 and their activating paths are close and they oppose each other, then multiple products are formed and it is difficult to guess which is major. For example, this. Now, this wants ortho para. This wants its ortho para. All are different sides and their activating paths are almost equal. So you will find that these two are better than the these two, because there will be steric hindrance there. Now, if the two groups belong to class 1 and their activating paths are close and they reinforce each other, again multiple products are formed. So here again, this is ortho para for OR. This is ortho para for NHCOR. Now, this is extremely unlikely due to steric hindrance. So again, you cannot guess which is major. And if the two groups belong to class 2, now this is what I was saying, with large difference in their deactivating nature and they oppose each other, then the major product is decided by the more deactivating group. Why? Look at this. Now remember, they both are deactivating ortho para. So NO2 deactivates its ortho and its para by a large amount. Whereas CHO is not activating these two. It is deactivating these two. Because CHO deactivates all positions. But it is deactivating its ortho para more, but not as much as NO2 is deactivating these two positions. So can you see NO2's deactivation is what counts? This position is highly deactivated by NO2. This position is highly deactivated by NO2. So it cannot enter these two positions, which are actually meta to CHO. So if CHO were to dictate, it should go to these positions. It doesn't. It goes according to NO2 because NO2 is a stronger deactivating group. So you will get meta to NO2 and of course steric hindrance plays. And if the two groups belong to class 2 and they reinforce each other, then almost entirely one product is obtained. Again, now here just look at NO2, look at its meta, only one meta is available and that also happens to be the meta of CHO. And the two groups belong to class 2 and their deactivating parts are close and they oppose each other, then not much product is formed because all positions are extremely deactivated. Look at this, how bad this group is. NO2 is highly deactivating its ortho para. NH3 plus is highly deactivating its ortho para. All positions are gone. If all positions are highly deactivated, you're not going to get any good result in this particular case. So that finishes off this particular video on effect of substituents. So that's it for this video. I hope this video helped you understand the effect of substituents. Watch it as many times as you want. And if you want to download the PDF of this particular presentation, you can visit chemistryuniverse.com. You'll find all PDFs of all the lessons that I've made so far. This electrophilic substitution will be available very soon in that website, because once the entire lesson is complete, then I'm going to upload all of them together. So the PDF will be available once I finish there's one more part to go, that is the in other aromatic rings, substitution in other aromatic rings, which will be done quickly. So probably by the end of this week, you'll be able to get the PDFs also of this. So you can go and visit chemistryuniverse.com, log in. You will have to sign up first, log in then, and then you'll be able to see courses. Go to JE class 11th and select organic chemistry, and then you can have a look at all of these videos. So far I've made up to electrophilic aromatic substitution. Once this lesson is over, we'll jump to alcohols. So anyway, we'll catch you up in the next video. Till then, goodbye and thanks for watching this.